Cool. All right. Hey, everyone. Welcome. Thanks for staying around for the last session. Hope you're sitting because this is going to be quite a long thing. So, title is Detection Engineering Setbacks and Some Rabbit Holes. I think the original title in the agenda was even longer, where I'm parsing ASM1 packets in Kusto, of course. I'm still going to do that. But stick with me. Of course, thanks to our sponsors. You've seen this slide several times. So, very brief intro. I'm Olaf. I work at Falcon Force. I do a lot of detection engineering, security research, all kinds of things blue. I'm a security MVP, and I used to be a documentary photographer. So I'm quite visually oriented. And as Alex mentioned earlier, I have a sort of attention to detail kind of focus. And you'll notice that throughout the slides probably. So what can you expect? A lot of things, fast-paced flow through how I started to build the detection, failed several times. I'll share those as well because I think it's important for you to know. A lot of technical things and no AI this time, I promise. Also no graph, which was heavily available today, cool. But also very deep rabbit holes. And some of them I'll actually share with you up to a certain extent because we only have a small hour. So what is it about? So curb roasting. I wanted to build a curb roasting detection based on Defender for Endpoint Telemetry. And basically curb roasting, very nutshell discussion around it is it's an attacker that requests a service ticket. They will try to crack the ticket and actually use the password to log on to your environment, move laterally, right? So there's a lot of tools to do this. The most famous, commonly used ones are Rubius, Kakeo from Benjamin Delpy, Empire from the PowerShell Empire library, but there's way more, of course. Even some C2s have their own implementation. They all work in a slightly similar way. So now we focus primarily on Rubius, but you can apply this methodology to all of the other ones. So as I do, and I teach detection engineering quite frequently, so what we try to tell people is if there's publicly known source code for it, please spend some time reading through it. So one of the things also that I did with Rubius is I went to the source code, and at some point you see the highlighted section where the validity lifetime is set to a ridiculously far away timestamp, right? Somewhere in 2037, which also says a high Kakeo kind of thing. So he copied it from there, Will Schroeder, when he wrote this. And I assumed, hey, this is a weird thing, right? Because Kerberos tickets usually only have a lifetime of 10 days, maybe 30 days, sometimes even shorter. So this looked like a really cool indicator to me. So I started Googling around a little bit and basically searching on GitHub for that specific timestamp string. And I got quite some hits. And mostly from like, hey, Kakeo is there, Rubius is there, Scapy is there, which is also a often used offensive tool, not necessarily only for offensive work, and some other things. So I figured, okay, I'm onto something. I also found a lot of Chinese weird tools that I couldn't read because I can't read Chinese. So I started digging around a little bit. One of the cool things that Microsoft did at some point is they ported Zeek, which is a network inspection tool, formerly called Bro, to Windows. So it used to be a Linux-based tool. They ported it to Windows. And some of that data is actually available in Defender for Endpoint. So one of the action types that my eye fell on is the network signature inspected action type, which is basically indicating Zeek without saying it. One of them had a Kerberos TGS request field in there with a field that is called the sample packet content. And that piqued my interest a little bit, and I started looking at it because it was quite big, and it's basically what it's looking like there. So first thing I did is say this looks URL encoded, which it is. However, you can't decode that with Cousteau, sadly, because Cousteau only seems to work if it is full ASCII character URL encoded data. So if there is a character in there that doesn't fit the bill, it doesn't translate it at all or partially. So that data was still useless to me. So the highlighted section is basically the URL decoded string from there. So that was annoying, but that didn't let me stop me. I basically put it into CyberChef, I decoded it in the same way as I would have done in Cousteau, and then you get at least some more information. And especially at the end, I saw this very interesting string that was identical to the timestamp, right? So this is the same data, but then at least more legible. And going through there, I also looked at the raw event and I saw the same thing. So it was actually just readable. So I could easily get that out with everybody's favorite toy, regex. So what you can see here in the query, and I know I'm going through it extremely quick, I'm basically extracting that 14-digit string that ends on a Z somewhere towards the end of the packet. And then the highlighted section at the bottom, you can actually see that I'm extracting those timestamps. So I was like, hey, this is cool, this works. And this is in our lab environment, so there's quite a few of them. As I mentioned earlier, a normal ticket granting service request only asks for a validity of maybe 10 hours to 30 days. It depends a little bit on the implementation, but that's generally fine. And in some cases, we've seen 90 days. So we can still use that auto detection, right? So if we look at the current time, and if it exceeds that, if it's too far in the future, then I can generate an alert. Sounds simple, right? So I started looking at it. I started converting it to a date time. And Cousteau wasn't happy about that because it had sort of a different format that it expected, I thought. So I didn't let that stop me. I wrote a whole substring parsing function to get all the right properties out, put them together with a stringcat command into a expected format that it did, parse that to a date time, and then do my comparison. And that actually worked. Now you only see the results that have that long TGS time, basically. And that gave results, so I was happy. Then I actually looked a little bit longer at my query, and I realized that I could only have done that last sentence and didn't have to do all that other fancy stuff. So that was a lot of waste of time. I felt very silly, but that happens if you're in the heat of the thing and don't read always your query even properly. So it's just in there for your amusement. Everybody makes mistakes, and then after I cleaned it up, this is the query that actually worked. So I was like, okay, cool, let's test this at a client environment, because I think I am onto something now. So I ran it at a client environment, and I got a little bit more results than I hoped for. So it's like back to square one. So I still was curious, why is it set to this ridiculous timestamp, right? So I started doing a little bit of investigation. I found out that the Unix timestamp is 32 bits. So if you would calculate that, then the end of epoch or the Unix timestamp is basically somewhere January 2038. So at some point, some computers might have the Y2K bug, but then different. So by setting that expiration to 2037, they ensured that at least it won't get out of the end of time, so to say, at least computationally. So it's sort of an endless valid ticket. But I still didn't understand why they went for somewhere 2037 instead of just the end of time, January 19th and 2038. Because it wasn't a nice round number, right? It was 128 days, which makes sort of sense computationally, but then 26 minutes, 2 seconds was weird. So I reached out to Steve Seifers, who is, at least has been part of the Microsoft Kerberos implementation for quite a long time. And he had a similar answer to what I expected. It's sort of a randomly selected, nice looking number. even though Windows never has that, will have that issue because they use a 64-bit time interrupt for it. So it's primarily to be compatible with Linux, where they selected it. And then I started a little bit further. So next to it being hard-coded in a lot of Windows tools or attack tools, it also is part of some old SDK, and even in the leaked Windows source code in from the server 2003, you can also see that same field at the bottom right, where they also have that same example time field. So it's been in there for like decades, which is also why I saw it so much. So I thought maybe I can compare it to an initiating process or something like that, where I can look for anomalous processes only generating this Kerberos request. But sadly, there was no data there. So Defender for Endpoint doesn't log the initiating process ID or its parent ID. Allegedly, that is due to a bug where it sometimes represents the wrong information, so they disabled it not to have you lose trust in the numbers that you're seeing, but I'd rather have you have nothing than potentially untrustworthy data. So not satisfying, but understandable. So again, we have to wait for a fix, and we don't have a detection, maybe, or not. So I was going back through my CyberChef because I had the feeling there was more information there. And as you can see, there's quite a lot of fields still in the bottom right that we can just read, and then all the other stuff might also be useful. So I started thinking about what does a Kerberos ticket request contain. So it contains quite a lot of information, as you can see. And the output, I try to match some things in line, right? So we've seen that end time already. Of course, on the left it's different because I took it from some website. But we know at least the end time that it states, where it has the validity that it requests. We can also see who is it talking to and what kind of services it's accessing. That's basically what you see here, right? Highlighted. So we can see the service, we can see the endpoint, and we can see the realm or the domain. But we also have these ticket flags, and these are the most important in most cases. We have also in our training, we let people struggle a little bit to extract the ticket flags from the Active Directory logs. So this is sort of what I was hoping to reproduce now. So maybe this is in there because it came after like some of the other fields. So I assume maybe that's 705, is it? So I started looking up the documentation, as you do. All people read that, of course. At least in some cases you actually should. So one of the things in there is the Kerberos ticket options. These are actually really well documented. And definitely if you go into this, read it really well, especially the bit that is not highlighted, but in the middle where you can see in the table below, the most significant bit numbering is used. And this is very important because it's sometimes also leaves significant bits in these things. And then on the right, you can see all the ticket options, which you probably can't read now, but you can of course go to the documentation. They also list the most common values, right? So you see a hex representation of all those bit numbers, which I will fry your brain with in a second. So I took that 705, I converted it to binary, and then I also converted it to hex to see if it came up with a number that made sense, right? But as you saw in the previous screenshot, it's like 408 and then 10,000. Or 608, 10,010, these kinds of numbers, and now I see like like a way different number at least. So, and I started looking at other packets, and sometimes it's 0. So I was kind of frustrated because it was not it. Then I reached out to one of my coworkers, like, hey, I'm stuck, and I really think it's in there, but I don't know. So we started switching perspectives because it's just the way how you look at it, right? And screenshots are from Visualize Value, best Twitter account if you like these kinds of things. There's a lot of really nice interpretations, but that aside. So I went back to my trusty CyberChef. I URL decoded it, converted it to hex. And here I actually could see that number is in there, right? So the data is there. So that was really nice. I was very happy that my colleague pointed me into this direction. So now at least we know that we need to figure out a way to get this data out. That data. So I was happy, right? It's like, okay, let's do this. So after some fiddling around, we knew that it should be there somewhere, but it's not the same, right? You can see a 80 percentage, 80 percentage, so the 80,000 bit is in there, but then in front of that there's like an @, and this is also why the URL decode breaks, because it's not, it's a different kind of character. So this is something we need to fix. And this is the rabbit hole, one of the rabbit hole alerts. This is probably the biggest one, because now we need to understand how does a Kerberos packet look. Google is of course very helpful. So Steve Seifus has a couple of really good blogs that I can't read out because it's way too long, but it's extremely useful and explains a lot of the things about how the Kerberos protocol works and how all these packets are constructed. So he also explains it in little too much detail, which is a very useful resource. Another really good one, if you want to sometimes take a shortcut because it's too much reading, especially on the Windows side, is the Rust documentation. So in a lot of cases, the Rust people are very explicit in all their documentation, and they basically show you how an ASM1 packet is constructed. So which fields are in there, what's the length, and all these kinds of attributes, which is very useful if you want to build a parser, for instance, or understand the data format that we've been banging our hand against. And of course, we also have to look at the RFC. So in here you can also see that in the RFC they state that the messages for Kerberos can either be there encoded or bare encoded. And in this case, Microsoft opted for the bare encoding, which is basic encoding rules, which of course doesn't tell you a lot. But again, Google can help you out there, and there's quite a lot of good documentation about bare encoding. Basically how it works is it is a tag, a length, and then a value. And that's basically also represented in this diagram, right? So you get a tag, which is sort of a marker, like, hey, it starts here, it's this amount of bytes long, and the rest is your value. And the value can contain another set of those kind of fields. So you can sort of deconstruct any packet into these kinds of subsets. So of course that's what I did in a Notepad kind of like editor. And I started deconstructing it, at least from the request body downward, because I wasn't interested in all that other stuff for the detection I wanted to build, because I was only interested in the KDC options. So I started sort of segmenting it a little bit to at least understand, okay, where is it starting, how long is it, and can I do anything with that? So that's sort of what you can see here, right? That same number is mostly represented here with some additional overhead around it. So I also wrote a little graph for that, where we can see, okay, here's that tag or marker. Then you can see the frame length of 7 bits. Then you get another marker. Then you get the data length, or another frame length, depending on how you want to describe it. So that's 5 bits, and then you have the data. And this is the only bit that we actually need to care about, because that is what contains our ticket options. And here you can see that similar thing with the 80, 00, and in this case, the 10, and that @ sign. So reading the documentation further, we know that a ticket option field only is 32 bits, and the first bit, 2 bits bytes are basically fixed in zeros. So we only need to look at those 4 other ones. And in this case, it can also be a non-ASCII character. So we need to account for that when we're parsing it, because we can't take the last, 8 digits, or because then we're losing data. So, of course, we need to bring back our best friend regex, And this is where the rabbit holes go deeper. Because there's a couple of things now. If you look at this field, you can see that that header of that marker set is in there twice. And we know from experience at least, I still don't know why the other one is in there, that we need to have that second set. Because the first set is usually all zeros. The second set has the actual ticket options that have been granted. But we don't know always how long it is, because in this case you can see that the realm or domain, we can't predict that unless we write it specifically for one environment, but that's not how we work. So we need to figure out a way to actually calculate that in a better way. So we started also figuring out how to distinguish where the realm starts. But that initial bit is always the same. So we can always rely on the first marker, the frame length, and then the second marker. So we also wrote the regex for that. And of course, there's memes involved there because, yeah, sometimes I always have to document it immediately when I start writing these things, because a couple of days after, I really don't know what I was doing. So that's also what happened here. I think even my colleague wrote this one, so I didn't even do it, but it's beautiful, right? We can write a regex that now finds the second bit of that same end, where we can also mark the start and end of the realm, so we can know where our data set begins and where it ends. That's basically what we're trying to do. And this is where Kusto actually finally comes in again. So we can use the index of function in Kusto, maybe not that well known, but basically you can use that to find a starting point for your data set. So in this case, what you can see here is we look for the start of the KDC options, where we take an index of the string that we feed it. So that's basically that whole string that you saw over here. And we use the regex where we know this is our marker, this is the length of the field, the 07, the 03 is the second marker, and then we know that 5 bits after we want to capture. So that's 12 characters in total, so we do the plus 12 where that is our starting point. So right after that sequence of numbers. So we at least know that that's basically what that 1557 means, is that's like the 1557th character of that whole thing that we're feeding it. That's our index of. But we also need to know when it ends, right? So we just calculated, or at least built a regex to find the start of our realm marker. So we also use that same thing in this beautiful regex that you can see, where we are looking for the index of that. So the second instance of that initiating realm, and we put that as a start realm, and then putting it together, the first two lines is basically that, and then we look for all the data in between. So that's the last one, where we extend our Kerberos flags, we take the substring, we feed it the whole data set, and then we this basically get only the characters that are between the start of the KDC options and the start realm, and then deduct the other component of it. So we only take the amount of characters in between, and we get this beautiful looking new string, which is still URL encoded and still messy. And then we still need to take into account that second option field. So that's basically what we do here. We go over that same set again. If there is something in there, we take it. Otherwise, we use the value we already calculated. And then we actually start getting somewhere. So now we have the KRB flags here that only have that small subset of data that we actually need to care about. So now we can start decoding it. But again, as I mentioned earlier, they all need ASCII values, otherwise Kusto can't decode it. Hopefully I get an explanation later why that is the case, or that it's just the way it is. But Kusto likes hex. but it needs hex bytes. So we also need to prepend it with the OX, because if we could just give it a hex number without that prepend, it can't properly convert it. But that's easy, so we can fix that. And we want binary values because I promise you a bit mask comparison, so we're definitely going into that as well. So this is basically how we decode it. We use that if statement that we had before, but now we start looking at it that if it doesn't start with that percentage, we know it's not a properly URL encoded version anymore, so we need to do something with that. What we do there is we convert it to UTF-8, take the first digit of that, and then replace the string where we add a OX to it, and then we start doing all the binary shifts, which I will explain in a second, because that is much fun. And then in the end, we have to convert it to hex again, because we need to compare it to the documentation. Great fun. So at least we end up with numbers that you might still be familiar from the documentation, right? And probably I gave you so much information that you forgot, so we can compare it here. At the bottom, you still see that 408, 100, and then a 10, for instance. So now we start going into calculating these numbers, because we can, of course, just do a comparison between that hex number and the other hex number. But if an attacker adds anything to that in his request, then the number will be completely different. The detection will fail, even though still the right attributes are set to execute that attack. So that is brittle. So if you want a bit more robust, we have to basically calculate the binary number for these kinds of things and do a bitwise comparison. So on a bitwise comparison, you can just compare whether certain flags have been set or not. So how we do that is we have to get a 32-bit binary mask, and as we saw earlier, it's like the most significant bit is set. So that means that we don't calculate from the right. So bit 1 is not the most right bit, but it's the second to first left bit. So it's the most significant bit for that end. So that's also what you see in the table, is like it shifts from left to right instead of from right to left, because they use most significant bits in this case. So how that works is you can set a certain mask, and then you can compare it to what you would expect. So in this case, the top layer and the bottom layer are obviously different, and if you do a bitwise AND, you only get a result, so you get a 1 if both are set, because it is an AND, right? So top and bottom have to be a 1 to get a 1. If the other one is a 0, then you get a 0. Then you have bitwise OR, where either of the 1 has to be set. So either the top one or the bottom one has to be a 1 to get a 1. If they're both 0, you get 0. And then you have XOR, which we won't use, and then you have a NOT, which is, of course, the inverse. Then there is the concept of shifting a bit, which is as simple as it sounds. So you can shift left one position, for instance. So you can see on the left, we have 3 zeros, then a 1. And on the second side, we shifted it left 1 point, so it moved over 1 field. That's how simple it is. So if you do a shift left 2, it moves 2 positions. If you do a shift left 2 of 2 ones, they both move 2 positions. That's how it works. And we need this later to get certain positions to set the flag for the right field. And we need this because it is the most significant bit side. So it's not, bit 1 is not the first bit, it is the 33rd. And so we can now also calculate whether a flag is set with a certain bit mask. So if I get that hex code that we saw earlier and I want to know is a bit set, is the forwardable bit, for instance, set, I can basically do that, where I can say, here's the complete bit mask, I do a binary AND with what I expect, and it needs to be what I expect. And then I get either a yes or a no back. So in terms of examples, I can ask it like, hey, is the renewable flag set in bit mask OX9A? Or is the forwardable one set? So how that works is the bit mask for renewable is the 0x80, and that is represented in that binary mask that you see there, right? That's just how the binary shift works. So if I compare these two, I can see on the left side that there's like a 1 and a 1. So if I do a binary AND, I get a 1. So that's actually true. If I compare it to the forwardable one, where it's like the top or all the way to the right, so the first bit is set in my question, but not in the field that I feed it, right? So you can see at the 0x9A1 that the first bit is a 0. So a 0 and a 1 with a binary AND is a 0. So my result is 0 instead of what I expect, so it's not set. So in order to calculate these properly, we can use Cousteau to propagate all these variables. So we can set forwardable, which was the first bit in the documentation, so that we have to put that in position 1. And then we have to shift it 30 positions to get into the most significant bit, first bit. And we need to do that for all these other fields that we know might be relevant for our Cousteau detection. And why we know these are relevant is basically we go through the documentation and we analyzed several of those packets. And explaining all that to you would take even more time, so you have to assume that we did the work there. And now we can compare these kind of bit masks where we can ask it, hey, I get this in my log, the 408 and then all the zeros, and I want to compare it with if a forwardable flag is set or a renewable one is set. So we can also combine these things, right? Where we can say, hey, either this or that needs to be in there. And this is basically where we generate a new combined set of two flags that we want to compare against. So that's also possible. And basically, this is what it would look like. So if I would say, hey, do a binary shift left of 30 positions for forwardable and 23 for renewable, I can do a binary OR into the forward and renewable variable. And if I would print that, you would see that hex representation of it, if I would print it as hex. So that's just the way how it works on the back end. So you can at least check your work as well. If you're very confused, I also built a very simple web page where you can just click it together and it will give you both values. But you still need to understand how you can build this based on the documentation if you want to do this well. So, of course, we have to go back to our source code to understand how Rubius is doing this, to see if there is a detection possibility. So one of the things that they have in their source code is the highlighted line. Maybe a bit small, apologies for that, but you can see all the ticket options that they set. So you can see that they say canonical-localized, they say forwardable, and they set a couple of other ones, which are basically these. So they said forwardable, renewable, okay, and that is anomalous. No spoiler there. So one of the things that we can do now is we can set these fields, then we can make a Rubius variable that we call Rubius RCCS, where we can do a binary OR of all those, and then do all that fancy regex magic that you saw in the beginning. I'm actually going way quicker than I expected. And then we can do the same, so we need to extend that into an OX version again. We can do a binary comparison for the field that we have in our logs, compare that to the fields that we just created, and if it's in there, we will get a detection for Rubius. So this is only for Rubius. You can do the same with Impacket, with Kakeo, and a lot of these other tools, because they quite often use things that aren't natively done by Windows. I don't know why. Sometimes they need it for certain reasons, right? So the renewable bit is just to have better persistence. So it's an easier way for an attacker to actually abuse that ticket, and they don't assume that you were able to build a detection for this, which you saw wasn't very easy. You can do a similar thing based on the Active Directory logs actually, which is a lot easier because you don't have to do all that regex stuff and all the decryption or the decoding of it. But this is more fun, of course. And you don't always have access to that information, and now you can maybe even get it from two sites. So it's definitely worth your time to build a detection on it. So this is sort of the whole thing. That only is 45 lines, but it took me 3 days, and I probably had one of my colleagues also spent several hours on it. So it doesn't look like much, but it was a lot of work and a lot of lessons learned. So this is basically the way where we even go deeper and also look at CertiPy and some other tools, all based on this network inspected packet. What is also interesting to note is that the packet itself is also called a sample packet, which is a very apt name because it's not complete. It is a sample. The good thing is that the ticket options are always in there. The expiry time that turned out to be useless is always in there. But some of the other interesting bits, if I scroll back a little bit, that you could use. So in some cases, so here you see also LDAP and the endpoint where it gets the service ticket for. And sometimes you even see the username who requested it, so for which service account that ticket's request was granted. In this case, you don't see that account, evidently. You do see the service that it's requested for, but that's also not always in there. So it's I tried to build some detections based on those, but those are sort of useless if you only get that data 30% of the time. Ticket options are always in there, so that's still a reliable way of doing it if you want to go this route. At some point I'll also open source the detection because I can assume that you can't read it from the screen. It's a fun exercise to do and play with it. I also was interested in what else is in there because there's way more Zeek events. Turned out that most of them are really samples. And you can't really build anything substantial on it. One of the things that we have is a bot that monitors Custo documentation and configs for Defender for Endpoint. One of the things we found was an addition a couple of weeks ago, or months ago by now, where there is now also a Kerberos connection inspected. So that's my new rabbit hole, which I don't have here yet, but one of the interesting bits that you can see here is the cipher, which I know you can do RC4 or the RSA one, which might be interesting. The direction could be very interesting, and especially the ticket hash is very interesting. So one of the next things I probably plan on building is a detection where we can track a ticket hash, how it's used, so that we can also see, for instance, ticket replays and reuse. So that will be a very interesting next detection to look at if you are bored and want to dig into something. And despite my big amount of slides, I'm actually done already. So we have some time for questions before Johnny and Alex come back and close it off. No, there was too much info, I suspect. The level 9. Yeah, that's I know who that is. Yeah, so we have a class where we divide our detections based up in levels, and I made the joke to actually allow people in the training to go through this and try to detect it as a level 99, where usually we don't go below 5. And with all that regex stuff and the weird parsing annoyances that you can expect why this is a little bit more complicated than an average detection.
And there is also a nice comment. Whoa, did not expect to see Rust documentation on a KQL talk. So how did that happen?
Yeah, it's very interesting. I just learned that Custo now also is mostly built in Rust, which I didn't know. I thought, and part of the Windows kernel is And that's, I think, yeah, it's more and more. That it's really useful that they at least took the time to make this documentation, because in a lot of places it's very difficult to find, especially for Microsoft, like their special implementations that they use sometimes. This is the referenced one, where it goes into this depth. So usually you have to either reverse some other parser from somebody that already went through the pain, and this is rare. But if you also deal with a lot of internals on the Windows side with APIs, usually the Rust documentation is also extremely valuable, where at least Microsoft also documents that well, but there's more flexibility there. Yeah, thanks.